Welcome everyone to another video, another calculus video. We're going to be talking about limit laws today. And so what this section really is this is really the start of actual mathematically correct thinking. We've been doing things intuitively before this. We've been showing where things come from. We've been explaining, hey, this is how you can think about something, but we haven't really been proving anything. We haven't really been using mathematical theory, just intuition, just thinking, yeah, this looks like that. Well, starting in 2.3, and you may or may not like this, we're going to be doing things a little bit more concrete, a little bit more accurately, okay? And the way that we're going to do that is with something called limit laws. So these are laws, these are rules that have been proven to work. So you're not going to have to worry about missing something. You're not going to have to worry about, oh, did I think of everything that could happen? These laws are going to apply, okay? So we'll introduce these, and then this is going to be our first step on the road to more mathematical precision. So let's start by introducing some of them. So we've done two of them before, right? We've looked at these two in the last section, right? The limit of a variable as that, right? The limit of an input as the input approaches a number is just going to be that number. And the limit of a constant function is just itself. We've done these ones before, okay? The new stuff is in what the book calls Theorem 2.5, and I'm including on that Canvas sheet in the handouts. You can look to the bottom and see it under the resources section. These are all the laws. Now, I'm not going to have you write them all out. You can copy them into your notes if you want, or you can just use the handout. So let's kind of unpack these. I'm not going to go through all of this, but I just want to kind of explain what's happening here. So we're going to start at the beginning where it says, let f of x and g of x be defined for all. Let's just start with this first sentence. Let f of x, that's a function, and g of x, a different function, be defined for all x other than a over some open interval containing a. What does that mean? So we're just looking at a small piece. For a limit, we don't need to look at the whole thing. For a limit, we only have to look at a small thing. So for example, if I'm looking at, let's say I'm looking at a function that looks kind of like this. Remember, the function doesn't have to exist at the point for the limit to exist. The limit of this function as x approaches 1 is positive 1, even though the function itself is not defined. There's an open circle here. So when it says for all x not equal to a, it means it doesn't matter what happens at the point that we're looking at, right? This function could be defined at 1, 3 or something, right? The function, it doesn't matter what the function's doing there as far as the limit's concerned. Okay, so we're just looking at some area nearby some value of a. That's what that first sentence is kind of talking about. All right, and then L and M are just going to be the limits of f and g. Okay, so they're real numbers. We're not talking about infinity. These don't apply to infinity because infinity isn't numbers. Assume that L and M are real numbers, so the limit for f is L, and the limit for g is m. And c, little c is always going to be a constant. In this whole class, anytime you see little c, it's probably going to be a constant. So that gives us a bunch of these results, as long as we assume those pretty basic assumptions. So this first one, the sum law for the limits, look at that. It's basically saying the limit of two things added together is just the limits of each individual one added together. And again, this only holds true as long as these limits exist. If L and M don't exist, then we can't use this. And the same thing for difference, right? The difference law is almost exactly the same as the sum law, but again, now it's just subtraction. Constant multiple. If we multiply a function by a constant, then we can just take that constant out and evaluate the limit. The The product, if we have a limit of two things multiplied, well, we can just multiply their limits together. A quotient, two things divided, you can just divide their limits. As long as we're not dividing by 0. So when you get into some of these later ones, there are a couple smaller things that you're going to have to check. Make sure we're not dividing by 0. That's a good rule of thumb in math. All right. Power law. If I have an exponent, and specifically an exponent that's positive, and an integer meaning like 1, 2, 3, etc., then we can use exponents for the limit laws. And there's a root law as well. And then, again, there's some assumptions. Look at this first one. This root law, the limit of a root is the same as the root of the limit. So you can evaluate the limit and then take the square root afterwards, or the cubed root afterwards, as long as one of two things happens. If n is odd, then we can do this all the time. Right? This works for every limit as long as n is odd, because cubed roots, fifth roots, these have a big domain, right? There's not going to be a lot of problems with cubed roots and like fifth roots and seventh roots as long as the index is odd, n is odd. But remember that if n is even, like a square root, a fourth root, then it's only going to be real if it's the square root of a non-negative number. If it's the square root of something that's at least 0. If we're taking the square root of something that's negative, we're not going to be dealing with real numbers anymore. And this whole class is mostly going to be dealing with, I said this whole class and then mostly. Most of this class is going to be dealing with real numbers. Specifically when we deal with functions, we're going to be talking about real valued functions. Complex valued functions exist, but that's outside the scope of this class. That's honestly outside of the scope of complex functions, are outside probably anything offered at SPSCC. Anyway, so let's use some of these. All right. So it's finally note-taking time. Everyone loves taking notes. All right, use limit laws to find the following. Part A is going to be the limit as x approaches 3 of 4x plus 2. So again, we have all of those laws from that last page, all of the laws from the book to use. The laws say that when we're dealing with limits, we can add things together. It's a sum, we can subtract, we can multiply, we can use products, we can use quotients, and these last ones have a couple restrictions. So in order to use these limit laws, we're just gonna have to break this up into multiple tiny little pieces until it becomes something like we did in the previous section. Right? The previous section said if we get things down into x's or into numbers, then we can evaluate mathematically. Again, if we take a step back, this question is asking about the limit of a function, and the function is a line here. So the limit of a line, like we can evaluate that graphically pretty easily, but we're using limit laws. We're actually trying to get some practice proving some of these with mathematical results. All right. This example is going to be a little tedious, but it's good building blocks for the future. And this is the only tedious video for this section, in my opinion. All right, so we have to use the limit laws. We're going to start with the sum law, which says that if I have the limit of two things added together, we can add their individual limits together as long as everything exists, but we're good to go. Everything exists here. So the limit is x, this is equal to the limit as x approaches 3 of the first thing plus the limit as x approaches 3 of the second thing. Right? 4x plus 2. And we should note what law we're using. Right? This is the sum law. This is very important for these problems, to be writing down what we're doing. And again, we're not going to be doing this for a super long time, so just kind of grin and bear it if you hate writing so much. But we're trying to do mathematical proofs in this video. So the sum law says that we can do this because all of these limits exist. Next, we don't have a mathematical result for the limit of 4x, but we do have a mathematical result of the limit of x. That's how we started today. It's what we did in the last section. The limit of x is just going to be whatever that x is approaching. Okay, so we're next going to use the constant multiple law, this one down here, that we can factor out a constant from a limit and evaluate the limit that way. So this 4 can come out in front. That's what the constant multiple law tells us. So this is going to be 4 times the limit as x approaches 3 of x plus the limit as x approaches 3 of 2. And again, that's the constant multiple law. And make sure whenever you're using these laws that you have this handout or the book open, and make sure that, especially in these later cases, that we're not running into any troubles. We're not dividing by 0, we have positive integers, or we're not dealing with radicals that are resulting in non-real quantities. And last but not least, we can use the very first two things, right? We know how to evaluate each of these limits from section 2.2. All right, the limit of x, right? As x approaches 3, how does x behave? Well, as x approaches 3, x also approaches 3, right? It's the same thing. This becomes 4 times 3. And again, as x approaches 3, how does 2 behave? Well, 2 doesn't care what x is doing. 2 is always just going to be 2. All right. And so this is, I don't know, what do we call this one? Basic limit results. That's what this is called. All right. And all that's left is a little bit of algebra to clean things up. We're going to get 12 plus 2. I'm not going to do that in 2 steps. That's 14. So this limit equals 14, and for the first time, we've actually proven something about limits in this class. I think the first time. And this is a function 4x plus 2. We could look at this graphically as well. Y equals 4x plus 2. As x approaches 3, as x is approaching 3, what is y doing? As x is getting really close to 3, y is approaching 14. All right. And in this case, the function value also equals 14, but that's not a requirement for limits. We'll talk more about that later. Let's do one more tedious example, and then we're going to move on to the less tedious stuff. I'll go through this one a little quickly just to give you a little bit more exposure. There's nothing new in this example, so you can pause it and just use the last video if you'd like, or you can move on. But if you want some more information here, let's look at this one. The limit as x approaches 3 of 2x squared minus 3x plus 1 divided by x cubed plus 4. This one's going to take a while. All right, but in the next video, we're going to introduce a new limit law that makes this problem much quicker. This is a rational function, means it's a polynomial divided by another polynomial. Okay, so to start off, we have to use the quotient rule. All right, we have something divided by something else. We go over to the quotient rule and says, okay, the limit of a quotient is the quotient of the limits as long as that bottom is not equal to 0. So this, all right, so we're going to say, okay, this is equal to the limit as x goes to 3 of the numerator divided by the limit as x goes to 3 of the denominator, as long as that denominator is not 0. And kind of intuitively, we can see that it's not going to be 0. As x is approaching 3, this number is way bigger than 0, right? This denominator is only equal to 0 at like the negative cubed root of 4. All right. So yeah, we're way away from that. So it's going to be the limit of the top, 2x squared minus 3x plus 1, divided by the limit of the bottom. And again, let's be very clear about what we're doing. This is the quotient rule, which we can use since the denominator is way bigger than 0. The denominator is not 0. Not 0 anywhere near here. And then we just got to keep on using more and more rules. All right. So that's going to equal, in the top, we can use the sum and the difference rules. It's going to be the limit as x approaches 3 of the first thing minus the limit as x approaches 3 of the second thing plus the limit as x approaches 3 of 1. Yeah. So when I said this video can get a little tedious, you are seeing exactly what it is. But there's not that much of that. Okay. Silver lining. First thing on the bottom. And second thing on the bottom. And again, this is from the sum and product rules. And you do have to write these down for these problems. You do have to do it step by step. We're actually proving things, so we can't skip steps. All right, and then we just keep on going. On the top, we use a constant multiple rule, bring that 2 in front. This is 2 times the limit as x approaches 3 of x squared minus 3 times the limit as x approaches 3 of x. This last one we can evaluate, right? The last one, use that basic limit property. And on the bottom, we're going to use the power rule. Okay? And the power rule was one of those later ones. What was the requirement for the power rule? We can evaluate the limit with an exponent as long as the exponent's positive and an integer. Check our exponent. Yes, that's a positive integer. 3 is positive. 3 is also an integer. This is going to be the limit as x approaches 3 of x. And then we're going to cube that limit using our limit law. Again, this other limit down here is 4. Here we're using a lot of laws. We're using constant multiple. We're using that basic limit laws. And we're using the power rule. And again, with n equals 3 was our power rule. All right, we just keep on going. All right, I'm going to copy this actually to the next one. All right, we can use now the power rule on the first thing in the numerator. The limit as x goes to 3 of x. We can now use a basic limit law on the second one. This is 3 times this limit. What is this limit? As x approaches 3, x is approaching, well, 3. We still have that plus 1 at the end. And the bottom again, as x is approaching 3, x is approaching 3. It becomes 3, and then we still have that cubed from before. Now we're almost done. Again, this is power rule with n equals 2. And again, more of those basic laws. This again just becomes 3 times 2 cubed like before, minus a 9 plus a 1. And the bottom becomes 27 plus 4. We're almost done. Just a little bit of simplification. Again, this is our basic law. And then 2 times 9 is 18. Minus 9 plus 1 becomes a minus 8. Bottom becomes 31. Our answer is 10 over 31. We'll want to check our answer whenever we can. 10 over 31 is a bit odd. So it's especially a good idea to check this one if you're a little nervous. This was the problem. This was the function 2x squared minus 3x plus 1 divided by x cubed plus 4. And we're curious about what does this function do as x gets close to 3? Well, as x is getting close to 3, not pi, as x is getting close to 3, the function is getting to about 0.323. 10 over 31 is also 0.323. So the function is getting really close to a value. And we calculated that that limit, that value that it's getting really close to, should be 10 over 31. All right. So that's the limit. And that's how one way that you can mathematically prove this. In section 2.5, the real precise definition for a limit that we are skipping, there's an even messier way to prove these limit laws. So these limit laws are actually nice. These limit laws make us not have to do 2.5, which we're skipping anyway. All right, so these are already these are already a shortcut. But in the next video and the videos after that, we're going to talk about even more shortcuts because this shortcut is still pretty long, okay? So be very careful on these problems. They're good because it shows the foundation. It shows where these things come from. We're actually using mathematical properties and theorems to evaluate these limits instead of just intuition. But the fundamental, in my opinion, fundamental aspect of mathematics is to do less work. All right. So, people were like, well, okay, so this is true, but how can we extend this? How can we make this easier? How can we make it quicker? How can we use these building blocks to build something even better? And that's what we're doing in the next couple of videos. Okay. Let me know if you have any questions and good luck.